Okay. Um, yeah. So we will start a new topic today. I'll maybe today. Yeah. Let's start understand the basics and then yeah we can continue. So yeah. So this is multi-threading. I'm sure some of you have heard the name. So let us understand what is a thread. Let us start with what is a thread. So till now we have talked about processes and we have understood that process is a program in execution. Now let's extend that now. So more technically, process is a program in execution with a single thread of control. So control, I think we understand that like what is the next instruction to be executed or what is the instruction which has just been executed now. That is what we mean by control. And so suppose as we know that there is a something called the someone, let's say the kernel, needs to know what is the next instruction that a process will execute and what is the state of the process. So state means, okay, process state we have discussed in a bit more other context, like say running, waiting, etc. But here what I mean is that we know that here what I mean is as follows. We know that kernel often swaps out a process. That means kernel often. Okay, I'm using some wrong terms today. Sorry. Swap out has a different meaning, so that's not the correct thing. What I meant to say is often the kernel deallocates the CPU from a process. That means the process goes to the waiting state. And at some later point of time, the kernel must resume that process from that same point. For this, the kernel needs to store some information. What kind of information? That, yeah, what kind of information? We have discussed that, but still. So what do you think is needed what information is needed to exactly define from where a process should resume? Yes, register values, program counter, yes. And that includes it is included in registers values, but still, I mean, that includes the stack. So where is the stack? So the stack will contain all the local variables for functions and so on. So that needs to be remembered, right? Okay. So, okay. So let's remember this discussion because we will soon need it. So, okay. So a process is a thread of control. That means these things like the PC, the register states, the stack pointer, these are kind of a single copy is there. That defines the thread of control. Like where is the process executing now and what instruction will be executed next. Now, our modern OS allows a process to have multiple threads of control. Okay. So for an example, like say you are using a word processor. So if you see many things are happening kind of simultaneously, you might think. So that as you press a keystroke, some part of the process is reading your keystroke. Some part of the process is updating the display and automatically spell checking is going on, right? So maybe you are going on typing quite fast, but still you will see in say MS Word, spell checking going on. So the thing is, are all these done absolutely sequentially? Well, maybe not. Modern OSs enable processors to have multiple threads of control. What does it mean? Let's see. So what is a thread? Or how is a thread created? A thread you can consider a basic unit of CPU utilization. Just like till now what we were discussing about processes, you might think that applies to threads now. So just like we discuss these things, that a process has a process ID, and then we just discuss like register states PC. But now we say that a thread has all these things. So a thread has a unique thread ID, program counter, register set, stack, and so on. Okay. And this is the important part. This information is shared with, okay, some of this information is, sorry, some of the information in the process So a particular process has multiple threads. Some of the information of that process is shared among all the threads. For example, the code section, the data section, and other OS resources like open files. Okay, so basically we are talking about some information of a process being shared among all threads and some information being unique to all unique to each thread. For example, this part, thread ID, program counter, register set, and stack, this is unique to every thread. Okay, so this is unique to every thread. However, the code section, the data section, and other OS resources like open files, this is shared among all threads from the same process. Essentially, all threads of the same process share the same virtual memory address space. Virtual memory, we have not discussed this, but we will discuss it in a lot more detail later in the course. So let's show you some pictures from Galvin that will make things a bit more clear, I guess. You see, this is what we have discussed till now, a process. So a process has code, code segment, data segment, open files. It has registers, it has stack, and it has like the thread. That means, say the program counter defines the thread. What is the next instruction to be executed? Now we are telling what we have discussed till now. This is a single threaded process. But the OS allows now to have multi-threaded processes like this. So here you see this process has created 3 threads. The code, data, and files is shared among all threads. See, only one copy is there. So the code, data, file, open files, these are shared among all threads in the process. However, each thread has its own registers and stack. Registers would include the PC also. So each thread has its own registers and stack. So basically each thread is having its own thread of control. However, they are sharing the code segment, data, files, and so on. Okay. So of course, question is, why do you need threads? Why do you think we need threads? Any answers? So again, see, we already know how to create processes. Like we know how a parent can fork child process. So we might even, I mean, the process could have forked 3 children instead of having 3 threads. But still, why do you think threads are needed? Okay, Deep says event handling. Okay, but see, sure, threads can be used for event handling. But the specific question I was asking is, we already know how to fork processes. So maybe what could be done by 3 threads, a parent could also fork 3 children processes and do the same thing maybe. Still, why do we need threads? Yes, so that is one good answer by Deep. So basically, some data can be, so look at this picture again. अरे मैं क्लास पे हूँ, तुम म्यूट करो अपना. कहाँ पे हो? अच्छा. Okay, so yeah, so one reason is that sharing data between threads. See, this data is already shared between threads. Okay, and the same thing Nisarg has also said. This data is already, or these open files also, they are already shared among the threads. So think about it. We discussed this when a new process is being created. A lot of things needs to be done by the kernel because that process will be a completely different process. So the whole memory area has to be initiated, the same code data, those things need to be copied and so on. But here we don't need to do all these things. The data is already the data and the open files, even the code, they are already shared among all these threads in the same process. So then, creation of a thread becomes much faster. So that is exactly why we need threads. Let's see. Context switching among threads of the same process is faster. So the OS needs to reset or store less memory locations or registers. Also, responsiveness is better, which is important for interactive applications. So for example, maybe some part of the process is still busy, the interface still works. So maybe uh, uh, yeah, so let's give an example. I mean, I'm just making this up. I'm not sure if browsers run that way, but um, let's say you are loading a very heavy web page on the browser. And also that page is where you have to sign in. So often what is done is one thread downloads the web page. I mean, maybe there are lots of images, etc. So one thread downloads all those things. The other thread is helping you to sign in. So you don't have to wait for the whole page to download before you sign in. You can sign in even when the page is partially downloaded or the downloading is still going on. Right, so for interactive applications, this feature is very important, that even if a part of a process is busy, some other part of the process is still working. That is important. So threads give a better or a more efficient way of achieving that. Again, exactly the points that Deep and Nisarg mentioned. Resource sharing is better for peer threads. So many possible threads of activity in the same address space. Right, so, and since the data segment, the code segment, the open files, they are already shared, this is much more efficient than say IPC, like what we discussed, inter-process communication. These are much more efficient than that. Right. So because I mean, memory access is usually like, okay, I should not say that memory access is quicker, but in general, like if you use pipes, shared memory and so on, all these are system calls, remember. So every time you write something to a pipe or you try to read something from a pipe, etc., you need to do system calls. But here the threads are already sharing the same address space. Therefore, its resource sharing is easier. Like that if you just declare some global variables, we'll come to those details, but if you just declare some global variables in your program, all threads will be able to access them. Okay, so that is there. Also, thread creation is much faster. So process creation is heavyweight because almost the whole copy of the parent process has to be created. Whereas thread creation is much lightweight. In fact, it has been found out that creation of a thread can be 10 to 30 times faster than process creation. Also, this part we are not handling much in this course, but in a multiprocessor or multi-core architecture, threads give you better scalability. So now again, in this course, we are only focusing on a single processor system. But nowadays, I am sure you know that most processors are multiprocessor, multi-core architectures. So they are having threads can actually give you a lot of scalability and performance improvement. Okay. And how are threads used in the real world? Just some practical examples. Let's take 3 practical examples: a web browser, a web server, and an OS itself. So in a web browser, yeah, I mean that what I said. Say maybe a very heavy web page is loading, but that is the web page where you have to sign in also. So one thread may be retrieving the data of the pages. Another thread may be displaying your image, which is called rendering. So actually showing the image on the screen. The third thread may be waiting for your user input because you will sign in. Right? So these things can happen, like at least you will feel that they are happening in parallel. You don't have to wait for the whole page to load before signing in. Another example is a web server. So I guess you are designing some kinds of servers in your network course. So I'm sure you will get the idea that maybe you are using different processes, but can be done using threads also. So maybe one thread is accepting requests over the network. So it continues listening for new connection requests. And when a new connection request comes, a new thread is given to service that request. So exactly how we have discussed this thing using processes, the same thing can be done using threads also. And finally, the kernel itself, or the OS. So most OS kernels are actually multi-threaded, and several threads operate in the kernel. So each thread performs some task, let's say managing memory or managing devices or handling interrupts, etc. So again, the design of the kernel itself is in most cases multi-threaded. I don't think that a kernel does everything like one thread of execution which does everything. Because the kernel has to do a lot of things, if you understand, like managing memory, managing device, handling interrupt, scheduling, and many other things. So often there are multiple threads used in a kernel. Okay, and fine. So there are several multi-threading models. I won't go into details here, but yeah, I mean, just yeah, wait. Yeah, okay. Yeah. So one concept is so there are threads can be again in two levels, user and kernel. So user threads are managed by user level threads library. So for example, there are POSIX, pthreads library, Windows threads, Java threads, and so on. In this course, we will focus on POSIX threads a bit more. That is what is used in Linux or Unix. But feel free to look up about Windows and Java threads. But all these are kind of user level threads. So yeah, the library resides at the user level. Of course, that library has to make system calls, but at least the library is in the user level, just like your C standard library. Also, there are something called kernel threads, which are actually supported and managed by the kernel. So almost all general purpose operating systems use these kernel threads. And as you might have guessed, user threads will ultimately need kernel thread support. Okay, so like we'll come to how the mapping is done, but yes, user threads will usually need kernel thread support. So basically, there has to be some mapping between user threads and kernel threads. And different types of mapping are possible, like many-to-one, one-to-one, many-to-many. So let's say many-to-one kind of mapping. Many user level threads are mapped to a single kernel thread. So the user threads are managed by the thread library in the user space, and the kernel thread is managed by the kernel. Now this is important. So actually this model is not very popular nowadays, and this is the main reason. A blocking call by one thread causes all threads in that process to block. What is a blocking call? I guess most of you know this still. What is a blocking call? What is the blocking call? Yeah, basically, yes, that's all right. So some kind of call, like system call most probably, such that the process execution will be stopped until that blocking call happens. Okay. Okay. So Nisarg, what are some examples? Like unmute yourself. What are some examples of blocking calls?
The select call.
Okay, something simpler.
Wait.
Yeah, wait is a blocking call. Yeah, accept may also be a blocking call, what parts mentioned. Exactly, scanf. Think about simple things. Even an input can be a blocking call. Okay. Now, by the way, so that's a good answer, scanf. Yeah, I mean, don't forget simple things. Yeah. So just one thing that whether a call is blocking or not may actually depend on a few things. So, okay, since Aryan mentioned it, Aryan, can you unmute yourself? So, does scanf always block?
I think yes.
Is there any condition by which the process might not be blocked actually? I
Placing it
mean, the
inside a
process
select,
gives us scanf. So process calls scanf, but is there
using
any
it with
condition?
select and FDS set function.
Sorry.
Using it with select.
Okay, again, think simpler. Like, is it possible that a
File
process
redirection,
file redirection? What do you
input
mean?
redirection.
Yeah, yeah. Okay, see, maybe you are going towards the correct answer, but I would like the definite answer. Is there any way in which scanf might not block? Okay, Ravi has given the answer. Good.
Okay.
If the input buffer already has data, then scanf won't block. Okay. Scanf wants some input from standard in, or okay, you might redirect the input. But if whatever be it, the source, if that buffer already has data, scanf won't block. Similarly, wait, yeah, wait usually blocks. But we discussed this, that if a process wants to wait for a child, and before calling this wait, that child has actually terminated, then the wait call won't block. So basically all these blocking calls wait for some event. And if that event has already happened, then they might not block. Okay, so but yeah, so coming back to this many to one scenario, the main disadvantage of this scenario, many to one mapping between user threads and kernel threads is that if there is a blocking call by any one thread, then basically all the threads in this process will block because there is only one kernel thread servicing all these user threads. So that is why this is not very popular now, this mapping, this many to one. The other extreme, what would be very efficient is one to one. Like each user level thread maps to one kernel thread. But then there is a so it's very like very efficient in that way that yeah, if even if one thread makes a blocking system call, others can run. That way it is very good. However, that also means that for every user level thread creation, a kernel level thread has to be created. And that is problematic. Like the kernel also will most probably have some restrictions on the number of kernel threads that can be created. Right. So like you just cannot go on asking, asking for more threads. I mean, you just go on creating more threads and kernel will also have to create more threads. That, at some point would become more of an overhead for a kernel. So the kernel will probably have some restrictions on how many kernel threads you can. Okay, Animesh is asking, can users split a thread? So won't the blocking problem also happen? Sorry, I did not understand the question. Animesh, can you unmute?
So like in the previous many to one case, so there was one kernel thread and like multiple threads for that. So if let's say I have a user thread and I attach two threads to it, like multiple threads. So if
You were saying
one
you
of
have
those
one
threads are,
user thread, you have a user thread
so
and you
I'm
attach.
asking, so over here there are multiple user threads attached to a kernel thread. So let's say I have a user thread, so can I attach more threads to it? If so, won't the blocking problem reappear?
No,
That
no, wait.
in the
You are
many to
saying
one, similar to
you have a user level thread. You are talking about connecting multiple kernel threads to that.
No. Like I have like two questions. First question is that let's say I have a user level thread and I want, so can I like, like in the many to one case for one kernel level thread there are multiple user level threads. I'm asking, can I do the same for a user level thread? So if I have a user level thread, can I attach multiple user level threads to it, like
Okay, what do you
on
mean by
one level
attach?
deeper? So like similar, like I have one thread, so can I like split it further?
Oh, I see.
Thread.
So see, okay, see, if you write your program in that way, you can. I mean, see, I mean, let's say your process creates a thread. That thread creates more threads. Yeah, that
Yes,
is
yes,
possible.
exactly.
Yes, yes. Just like
So
we
so my
discussed
my
that.
question being that,
Just a sec.
so
So we discussed this while discussing about process creation. There can be a whole tree of processes, like one parent process creates two child processes. Those child processes create more child processes and so on. So similarly, that can happen for threads also. Yes, now go on.
so the second part being that if so now that this is possible, so if let's say in the tree of user threads, even like, that problem will again reappear, that if one of the threads is blocked, the entire thing would be blocked.
That
I mean, it
depends on
won't be as
how.
bad as the many to one thing, but the problem is still there, right? If it is a problem.
See, that blocking problem may be there, but I don't understand the relationship between, I mean, okay, I don't understand the difference between the scenario you are talking and the scenario shown on the slide, because how your process is handling the user level threads, that's your decision. So suppose you now have 50 threads, whether all those were created by one parent process, or you that parent process had created a few threads and those other threads created other threads. I I mean, how is that different from the perspective of a
Uh,
kernel mapping?
Yes, so exactly. So the problem that the many to one model face, that even if one of the blogging call by one thread causes all threads in the process to block, so that problem is still there in this system as well, right?
Yeah, yeah,
But
it
it's
is.
like
It is.
one level deeper instead.
Okay, sure. I mean, yeah, you can say that. But yeah, okay. I mean, yes, I mean, I don't see much of a difference from a kernel level, but yes, you are right that the same problems exist in both situations. Okay, I see a question by Nisarg, but I'll come to it. Just let me just complete one more slide, then I can leave it. Yeah. So this is one another extreme, one to one, as I said, much more efficient. Why? Because like every kernel, I mean every user level thread has its own kernel level thread, but then there are restrictions on how many kernel threads can be created. Last, the many to many model. That means several user level threads map to several kernel level threads. So let's say the kernel creates a fixed number of threads, and then all those, I mean, those are used to handle different user level threads in some with some mapping. So at least if one thread, say one thread, one user level thread performs a blocking system call, then maybe one of the kernel threads will be blocked, but the others can continue execution. Right. So this is again, this is, I mean, this usually happens in Windows. This is not very common. So like, yeah, I mean, yes. So all these different thread models, like how will user threads be mapped to kernel threads, that again is decided by the kernel's designers. So we are not going into much details about those things in this course. Okay, next comes the POSIX pthread library, which we will continue tomorrow. So in general, I'll stop here. I'll just take Nisarg's question. Yeah, others feel free to leave. Like, yeah. So yeah, Nisarg, you are telling about that blocking thing, I guess. So again, see, whatever be it, it's a system call, right? So say scanf or wait. So ultimately a system call happens. Now yes, at some level it will be checked that whether the buffer, let's talk about in scanf, whether the buffer already has data. If so, then this process will not be kept in the waiting state, etc. Maybe uh, it will be allowed to execute. Okay. So yeah, I mean, uh, I understand your question. You are going into the detail about whether, I mean, when to say is the process blocked? Like the moment it has made a system call is then it is called blocked, or like the kernel does some checks to understand if there is buffer, etc., and then decides whether to block or not. This I'll have to look up also. This I'm also not sure. The answer may be different for different calls. Like scanf and wait may not always be handled in the same way. Because in scanf, if you do a scanf, okay, maybe we should not compare scanf and wait. We should compare read and wait. Okay, so yeah, suppose you have you should read or wait, then sure, someone needs to decide whether the system needs to block, sorry, whether the process needs to block or not. The kernel will do that. The question is, I would imagine that if there is already buffer in the data, or if there is already data in that buffer, or if maybe in case of wait, if the child has already terminated, then the process won't be blocked. But yeah, I mean, maybe the exact details I'll have to look up. Okay. Does anyone here want to add anything to Anisar's question? You can unmute and say, Anisar, yourself or someone else. Okay, not. Do try to find the answer. I'll try also. So my hunch would be it is not blocked. I mean, some check is performed, and if necessary, only then it is blocked. But yeah, I mean, would be nice to know the details. Fine, I'll stop here today. We'll continue tomorrow. Best of luck for your DBMS lab test.